AI security is not just about protecting a model. It means securing the data, pipelines, prompts, APIs, users, and suppliers around it. In this lesson, we'll turn AI threats into practical architecture controls and evidence. So far, we've built from ISO 42001 foundations into governance, architecture, and governed operations. Now we focus on protecting those environments. Security architecture and threat management turn policies and controls into defenses against real attack paths, before we move into incident response. In ISO IEC 1421, AI security begins with risk and impact. What could go wrong, who could be affected, and which obligations apply. Those risks then shape architecture decisions across data, models, prompts, APIs, infrastructure, pipelines, and human touchpoints. Controls need to be preventive, detective, corrective, and governed, not just technical. Monitoring and audit evidence close the loop, showing that controls work, exceptions are managed, and lessons feed continuous improvement. AI changes the threat model because the system is no longer just code and infrastructure. The model, the data behind it, and the way users interact with it all become attack surfaces. Traditional risks still matter, including exposed APIs, weak access controls, and vulnerable dependencies. But AI adds new paths. Poisoned training data, stolen or reverse-engineered models, prompts that override instructions, retrieval content that manipulates answers, and third-party models you cannot fully inspect. A useful mental model is to ask, what could corrupt the data, manipulate the model, abuse the interaction layer, or compromise the supply chain? Data attacks usually target two things: integrity and privacy. With poisoning, the attacker changes what the system learns by inserting malicious examples into training, fine-tuning, feedback, or retrieval data. With inversion, they use model outputs to reconstruct sensitive details the model may have absorbed. With membership inference, they test whether a person or record was included in training. The defense is not a single control. It is a data architecture: lineage, validation, access limits, sensitive data scanning, retention rules, and privacy-preserving methods built into the lifecycle. Model-centric attacks focus on the model's behavior, not just the application around it. An attacker may probe inputs and observe responses. With adversarial examples, tiny changes can push a classifier toward the wrong answer or bypass a safety filter. With evasion, the attacker keeps adapting until detection fails. With extraction, repeated queries reveal enough input-output patterns to approximate the model itself. Defenses work best when they interrupt this chain early and often. Input validation, adversarial testing, query limits, output monitoring, watermarking, and protected inference endpoints. Generative AI adds a distinctive risk. Instructions are now data. A malicious sentence in a document, web page, ticket, or chat can become a command the model treats as relevant. Prompt injection tries to override the intended hierarchy of instructions. Jailbreaks push the model to ignore safety, role, or confidentiality boundaries. Tool abuse is where the risk becomes operational, because the model may call APIs, query data, send email, or trigger workflows. The control mindset is to separate trust zones, validate retrieved content, authorize every tool action, filter outputs, enforce policy outside the model, and require human approval for high-impact steps. Risk also extends beyond the product you build. Modern AI systems inherit exposure from datasets, pre-trained models, APIs, packages, containers, orchestration tools, and SaaS providers. Any one of these can introduce vulnerabilities, licensing issues, bias, privacy exposure, or unclear provenance. The practical control is supply chain governance. Know which sources are approved, assess components before use, set contractual expectations for data handling and security, and monitor changes over time. Trustworthiness depends not only on your model, but on every dependency it relies on. The strongest AI security architectures use layered defense, not a single control point. Each layer reduces a different failure mode. Identity and API controls limit who can ask the system to do what. Data and training controls reduce poisoning, leakage, and unsafe lineage. Model serving controls protect weights, prompts, and inference endpoints. Compute controls harden the runtime where code, tools, and agents execute. Monitoring makes unusual queries, drift, abuse, and exfiltration attempts visible. Governance and deployment controls make change safer, with approvals, baselines, rollback, and evidence. The goal is that no single weakness compromises the whole AI system. AI workloads expand the identity problem. It is not just people signing into an application. Notebooks, pipelines, service accounts, agents, vector stores, and inference APIs all need carefully bounded permissions. Start with least privilege, using roles or attributes that match the job. Prefer strong authentication, workload identities, and short-lived credentials over long-lived keys. Separate who develops, validates, approves, and releases models. For agents and tools, define explicit scopes, action limits, and approval gates. Then keep reviewing access, especially privileged accounts and third-party integrations. Every AI surface should be treated as a controlled boundary. Development, training, inference, production, and sensitive data should be segmented so a compromise in one area cannot easily move laterally. External traffic should pass through gateways that enforce authentication, authorization, schemas, input checks, rate limits, and abuse detection. Higher risk behaviors such as plugins, notebooks, agents, tool calls, and code execution belong inside sandboxes with tight permissions. Running workloads also need protection. Hardened containers, endpoint detection, vulnerability management, and secure baselines across cloud, data, and edge environments. Sensitive data can move through many parts of an AI system. It may sit in datasets, embeddings, model artifacts, logs, backups, and vendor services. Encrypted at rest, in transit, and in specialized stores like vector databases. Keep secrets out of code and notebooks. API keys, tokens, certificates, and provider credentials belong in managed vaults with rotation and tight access. Then reduce exposure at the data level. Classify inputs and outputs, mask or tokenize sensitive fields, redact prompts and responses, enforce retention, and delete securely. Strong controls make leaks harder and breaches smaller. Controls only matter if we can see them operating. Start by collecting standard security telemetry from gateways, identity systems, model serving, cloud infrastructure, data stores, and pipelines. Then add AI-specific signals. Prompt injection language, jailbreak attempts, unusual token spikes, repeated probing, unexpected tool calls, retrieval anomalies, and possible model extraction. These events should feed the same triage path as other incidents through SEM, SOAR, dashboards, and response owners. Preserve the evidence as well. ISO 420D-1 requires proof that controls ran, alerts were reviewed, incidents were handled, and corrective actions were completed. Model protection starts before deployment, by proving where every artifact came from and whether it can be trusted. Capture training data references, code version, hyperparameters, evaluation results, approvals, and intended use limits. Control the software supply chain with SBOMs, pin dependencies, license checks, vulnerability scans, and patching. Before release, protect the artifact itself with checksums, signatures, trusted registries, access controls, and immutable records. Third-party models need the same scrutiny: security review, privacy assessment, contract controls, and monitoring. The goal is a controlled path from source to runtime. The key message is this: secure AI starts with architecture, but it cannot stop there. We protect data, models, prompts, APIs, pipelines, infrastructure, vendors, and users with layered controls. We also plan for AI-specific attacks like poisoning, extraction, prompt injection, and jailbreaks. Next, we turn those controls into incident detection, escalation, containment, recovery, and evidence.